All right. Hello, everyone, and welcome to our 9th lesson in Unit 3, which is on separations of solutions and mixtures. So in this section, we're looking at how intermolecular forces affect the way mixtures can be separated. So the key idea for this lesson is that solutions can't just be separated by simple filtration. They instead require different methods that are going to take advantage of their differences in intermolecular interactions. So by understanding these interactions, we can explain the results of different separation techniques and why certain processes work for different types of mixtures. This slide shows different ways we can separate solutes from solvents. Remember, solvent is what is doing the dissolving and solute is what is being dissolved. Each method works because of physical properties and differences in intermolecular forces. So for example, magnetic attraction separates magnetic from non-magnetic materials. Filtration removes a solid from a liquid. Crystallization pulls a solid out of a solution, and distillation methods separate liquids based on boiling points. Finally, we also have our chromatography, which separates different substances from a solution depending on how they interact with the stationary phase, which we will talk about in a later slide. Evaporation is one of the simplest ways to separate a solid dissolved in a liquid. In this process, the solution is heated until the liquid boils away, which leaves the solid solute behind. For example, if we heat a solution of water and salt, eventually that water is going to evaporate and all we're going to be left with is the solid particles of salt. So essentially it's just boiling off the liquid to isolate the solid. Filtration is used to separate an insoluble solid from a liquid. So the mixture is going to be poured through filter paper, which acts as a porous barrier, and the liquid is going to pass through as the filtrate, while the solid gets trapped in the filter as residue. This only is going to work if you have an insoluble substance. For example, if we're looking at a mixture of water and sand, in order to get that sand out, we can put that solution through a funnel with filter paper and only the water is going to pass through. So now we're left with only sand and water. Now let's say that was a mixture of water, salt, and sand. Because salt dissolves into water, if we put that through filter paper, the filter paper is only going to catch the sand, and in the filtrate you're going to have water and salt that is dissolved. So then you'd have to take an additional step if you wanted to remove the salt from the water. All chromatography methods use two parts, a stationary phase and a mobile phase. In paper chromatography, the paper is the stationary phase and the solvent is the mobile phase. So as the solvent moves up the paper, each component of that mixture is going to interact differently. Some are going to travel further because they're more attracted to the solvent, and some are going to stay closer to the paper because they're more attracted to that stationary phase. The difference is going to allow the mixture to separate into distinct spots, like in the picture where it's separating the dye of the black ink into its separate components. Paper chromatography is a simple and inexpensive way to separate mixtures. A small drop of the sample is placed on that chromatography paper, and then we place the chromatography paper in solvent, and as the solvent moves up the paper by capillary action, it's going to carry the compounds with it. Now, if you don't remember capillary action, remember it's the process where liquid moves upward or through a narrow space without being pushed by external forces. So it's going to happen between two different forces, either cohesion or adhesion. Remember, cohesion is the attraction between liquid molecules, which means they just stick together. And adhesion is attraction between liquid molecules and the surface. So chromatography is going to be adhesion that pulls the solvent up the paper fibers, and then cohesion is going to drag the other solvent molecules along with it. So that's why the solvent climbs up the paper carrying the dissolved substances. So different compounds are going to travel at different speeds and different lengths depending on how strongly they interact with the paper. So that difference is going to allow us to separate and identify the substances in the mixture. In paper chromatography, the components of a mixture separate because they travel different distances up the paper. So to analyze the separation, we use what's called an RF value, which compares how far each component moves relative to the solvent front. And the solvent front is just from the baseline to as far as the solvent travels. So the formula is the distance traveled by the component divided by the distance traveled by the solvent. So each compound is going to have a unique RF value under set conditions, which makes this a useful way to identify substances. So if we're looking at this example on the right here, we can see they all started at the baseline, which is this line here. So this is where we would start to measure. And then we can see that the solvent traveled all the way up to the solvent front, which is here. So this would be our denominator value, the distance from the baseline to the solvent front. And then in the numerator, we would have our distance traveled by the component. So let's say we're talking about this green dye. We would use the distance from the baseline to the center of our dye, in this case the green one, which would be a value of B. So in order to get our RF value, we would take B and divide it by A. All right, so we went through paper chromatography. The next type of chromatography we're going to talk about is TLC, or thin layer chromatography. It's very similar, but instead of paper, it's going to use a thin layer of material, and usually that material is silica. So the silica, in this case, would be the stationary phase, while the solvent will still act as the mobile phase. So compounds are going to move at different rates depending on their polarity. Polar molecules are going to stick to the plate more and move less, while nonpolar compounds travel further with the solvent. So you might be asking, well, why would the polar molecules stick to the plate and not move as much? Well, that's because silica, the stationary phase, is polar. And because it's polar, it means it has strong attractions with polar molecules. So if your component within your dye or whatever you're testing on this TLC is polar, it's going to want to stick to that silica and it's not going to move as much. Nonpolar compounds don't interact with that silica. In fact, they're going to interact more with the solvent, which is nonpolar. And since the solvent is flowing up the plate, nonpolar molecules are going to travel further and faster. So in short, polar molecules move less and they have a stronger attraction to silica, and nonpolar molecules move more and travel with the solvent. All right, so the first two types of chromatography, we had some sort of material and the solvent was moving upward along the material. In column chromatography, we have a glass column that is filled with a stationary phase, and we are putting the sample on top and letting gravity move that sample through the stationary phase. So this one is a little bit different. The main difference with column chromatography is you can actually collect your sample because it's in a certain material in which it's collectible. So just to briefly summarize column chromatography, a solvent or a mobile phase is going to carry the mixture through the column. Compounds that interact weakly with the stationary phase are going to move through faster, while those with stronger interactions are going to move more slowly. And as a result, the different compounds separate into layers, and then they can be collected individually as they leave the column. All right, so before we move on to distillation, let's do a few practice questions with chromatography. The diagram above shows thin layer chromatograms of the same mixture of two compounds. Based on the chromatograms, which solvent would be most effective at separating the two compounds if the same stationary phase is used for column chromatography? So on a TLC plate, if the spots are too close, then there is pore separation, which means in a column, those fractions are going to be overlapping and it's not going to show very well in column chromatography. So really, solvent A, B, and D are all very close to each other, which means it's going to make for a very hard column chromatography because we're not going to be able to see where those individual components are lying. However, in solvent C, the two compounds are going to travel at different rates and there is a clear separation in the middle of the plate. So in column chromatography, that means they will come out as separate fractions rather than mixed between fractions. So the answer for this question would be C. The diagram above shows a thin layer chromatogram of a mixture of polar products from a chemical reaction. The separation was performed using 50% ethyl acetate and hexane as the solvent, and silica gel as the polar stationary phase. On the basis of the chromatogram and the information about the solvents in the table, which of the following would be the best way to decrease the distance that the polar product travels up the plate? So we already know that the material for the TLC is silica gel, and we know silica gel is polar, which means it holds polar products strongly. However, you can see our product traveled pretty far up the solvent front, which means we also have a polar solvent. So because our current mobile phase is 50% ethyl acetate is much more polar than hexane, which means our polar products are also going to travel with that ethyl acetate. So to make the spots travel less, you need a less polar mobile phase so that the polar compounds stick to the silica more than the solvent. So A says use pentane instead of hexane. Well, pentane and hexane are both non-polar solvents, and we still have our 50% ethyl acetate, so that doesn't actually solve the problem. B says decrease the percentage of ethyl acetate in the solvent. I think that would be a great option because by decreasing the ethyl acetate, we would make the solvent less polar. And by making it less polar, our product is more likely to stick to the polar silica. So B would be our answer for this question. A chemist conducts a column chromatography experiment by placing an aqueous mixture of X and Z into a column that is packed with a non-polar stationary phase. After ethanol is poured through the column, separation of X and Z occurs as shown in the following diagram. So we know ethanol is a very polar molecule because it has hydrogen bonding. So if we look at our final column chromatography, we can see the triangles went through the column with our polar solvent, which is ethanol. And because like dissolves like, we know that Z is polar. And because X wanted to stay with the non-polar stationary phase, we know that X is also non-polar. So our final separation technique is distillation. It's going to separate liquids based off different boiling points. So if you are ever looking at distillation as a separation technique, just make sure you have a mixture of liquids and they have different boiling points. A liquid with weaker intermolecular forces is going to boil at a lower temperature and then vaporize first, while stronger attractions lead to a higher boiling point and that liquid will be left behind in the original glassware. Looking at this example on the bottom here, we have a solution of ethanol and water. Water molecules have very strong intermolecular forces with hydrogen bonding, so they boil at 100 degrees Celsius. Ethanol, on the other hand, has weak intermolecular forces and a lower boiling point around 74 degrees. So when we heat a mixture of ethanol and water, the ethanol is going to vaporize first, and that vapor is going to be collected, cooled, and condensed into a separate container as the distillate. So here we have ethanol over here. This would be known as the distillate. The water, with its higher boiling point, mostly stays behind in the original container, and this is how distillation separates those two liquids just based on their volatility or their boiling point. All right, let's wrap up this video with a couple practice questions. So this one says, a student obtains a mixture of the liquids hexane and octane, which are miscible in all proportions. Mixable just means that they mix together. Which of the following techniques would be best for separating the two components of the mixture and why? So I wanted to give you an opportunity to think on how you would answer this as a free response question. This specific question was multiple choice, but I do want you to practice writing this answer down as a free response question, and then we'll go over it. So the first part of this question is that the liquids can mix with each other. And because they can mix with each other, we now have a solution of liquids. And because these two liquids have drastically different boiling points, that means we can use distillation to separate the hexane and the octane. So if we were to put our solution under heat and collect the vapors, we would obviously be collecting hexane first because it has a lower boiling point, and then the octane would be left behind. All right, and for our last question of this lesson, a student obtains a liquid sample of green food coloring that is known to contain a mixture of two solid pigments dissolved in an aqueous solution of ethanol. Which of the following laboratory setups is most appropriate for the student to use in order to separate and collect a sample of each of the two pigments? So the first thing I want to go over is that it says a liquid sample, which means we are not using filtration because there is not an insoluble solid that we can collect in the filter paper. Then we have pigments. Now, when I see the word pigment, I'm going to go directly to chromatography, so I know I'm not using distillation. And the last thing is when it says collect a substantial sample. Whenever I need to collect pigment, I'm going to be using column chromatography. So it's going to be the best option because it separates large amounts of compounds based on its polarity or affinity, and you can collect fractions of each pigment as they go through their mobile phase. All right, I hope you have a great day.